like a very good hand in poker, there's a chance that your opponent has an even better hand by chance. So even if it makes sense to like gamble on a very good hand, it's still possible that you'll lose that round. And in the case of poker, when you bet wrong and you lose money on a hand, that is an example, that is equivalent to a decision error in statistics, where in poker, your decision is you either kind of go with the hand or you fold. The decisions in statistics with the null hypothesis significance test we learned about are you reject the null hypothesis or you fail to reject the null hypothesis. And there are two different errors that you can make. There is one error, well, we'll get to this in a second, but just because you have made a decision error doesn't mean you've done something wrong. That's just the nature of probability. And what the p-value or the alpha value actually means is it is the amount of sort of error of a certain type you're willing to accept, the rate of a certain type of error that you're just willing to accept. So if you set your significance threshold, what we called alpha, but if you call it p, it's fine as well, and just make sure that you're talking about a threshold rather than a p-value of a sample mean. If you set the alpha value or p-value to 0.05, you're actually saying this, you're fine with a 5% chance that you'll reject the null hypothesis even if the sample was taken from a distribution that had the characteristics of the null hypothesis. So even if the null hypothesis was true, you are going to reject it 5% of the time. And that's an error because the result of the test was that you rejected the null hypothesis. And so there are two kinds of error. There's the type 1 error, and there are type 2 errors. Type 1 errors are the kind of errors that we were just talking about, where you reject the null hypothesis when the null hypothesis is actually true. And this is called a false positive because in the context of statistics, when you reject the null hypothesis, it's often just considered like a hit or a positive thing. It's often the more interesting finding when you reject the null hypothesis because it means there's likely to be an effect, and it's always more interesting when there's an effect than there's not. But when you reject the null, when you should have failed to reject the null, that's a false positive. Type 2 errors are the converse, where you fail to reject the null, but the null hypothesis is actually false, and you should have rejected it. Or in reality, the null hypothesis was false. And this is a false negative. And in general, it's considered better to get false negatives than it is to get a false positive. Because in the context of, let's say, psych research, if you get a false positive, you might, on a study of social psychology, you find like a very interesting sort of effect of like social contagion or something, some kind of interesting effect that you want to publish in a journal, you want to go to a conference and tell everybody about, you want to do a TED Talk about it. You can go out into the world and spread misinformation because you think that you found a real effect because you've rejected the null hypothesis in your experiment, but in fact, the null hypothesis was true the whole time, and that's a big problem because you're spreading misinformation and you're wasting your own time. Whereas if you do an experiment and there is in fact an effect there, but you simply fail to find it through chance alone, a type 2 error, it's not such a big deal because you'll just go, oh well, that didn't work out, I'll try something else. And I really like this illustration diagram over on the right side of the page because what you have is the 4 possible states of the world. You have when you have half of these quadrants is when you come to the correct conclusion after a hypothesis test. So in the top left, we have the true state of the world, true state of reality is that the null hypothesis is true. And your conclusion from doing the null hypothesis significance test, the statistical procedure, is that you accept the null, or you fail to reject the null would be the better way to put it. I should probably erase that. You never accept the null, you always just fail to reject it. Anyway, but this would be a correct conclusion because nature is in nature, in reality, it actually is true. The null is actually true, and that's the conclusion you came to. Alternatively, the actual state of the world is that the null hypothesis is false and should be rejected. And if you do reject the null hypothesis in that situation, that is also a correct conclusion. And that type 1 and type 2 errors are the other half of this distribution here, or this 4-quadrant model. So type 1 errors are where the true state of the world is that the null hypothesis is true, there is no effect, there's no difference between groups, depending on the kind of study you're doing, but you reject the null hypothesis anyway. And then the alternative is a type 2 error, where in reality, the null hypothesis is false, and you should reject it. If in a perfect world, you would reject it. But due to random chance, you fail to reject the null, and you get a type 2 error. So understanding the difference between type 1 error and type 2 error is very important. And the bigger problem in our kind of research is type 1 error. We're generally pretty happy with type 2 errors because they don't cause as much of an issue. Type 1 errors cause a lot of issues. So previously, we talked about setting a significance threshold. So the two examples of significance thresholds that we talked about being the conventional limits are 0.05 and 0.01. These are also called the type 1 error rates. So 0.05, 5% error rate, 0.01, 1% error rate. This refers to the chance in a given experiment you will make a type 1 error. So just think about that for a second. Let's say every single researcher in the world chooses an alpha value of 0.05. And let's say let's say there are only 100 researchers in the world, and all of them sort of do experiments. And if 100 researchers do 100 experiments, 5% of the time, they are going to get a type 1 error. So 5% of the time, there will be researchers who are saying, I have a significant result, I found an effect, or I found a difference between groups. But those 5% of researchers will be wrong because they will have made a type 1 error. If you think about all of the experiments that are being done in the world, I can tell you a very, very tiny fraction of experiments that are actually performed end up getting published. There's this very, very strong filtering effect where only the findings that are interesting get published in journals, and the findings that fail to find an effect, and when I say fail to find an effect, I am almost always referring to a study that fails to reject the null hypothesis. Those studies simply don't get published. I mean, I defy you to find a psychology research paper that does a bunch of statistical tests and finds no statistical and reports no statistically significant results. I'm pretty sure there's just none out there, because if you're the editor of a science journal, you care about publishing interesting cutting-edge research, and you don't care about research that just finds what people already know or finds that there isn't an effect. So the fact that most research being published is claiming to have rejected the null hypothesis in at least one of their statistical tests, and we know that if they use a 0.05 significance threshold or alpha value, that just without any kind of filtering, so that a majority of the published results are rejecting the null hypothesis, you can just expect a fairly high rate of false positives in published research. And that is, in fact, what is found when people try to replicate published research. So there's this really, really bad incentive to, if you choose a alpha value of 0.05 or even 0.01, you're going to end up with a lot of research that is false. Research that, in terms of where it is on the quadrant here, in reality, there is no effect, and the null hypothesis is true. But the conclusion from the statistical analysis is that there is an effect, and that's what gets published. And that's leaving aside all of the incentives researchers have to simply make up findings or kind of massage the data they have so that it moves over from the fail to reject quadrant into the reject quadrant. A lot of that happens as well. So type 2 errors, you're going to be hearing less about them. You're probably going to never hear about them again after I discuss them in the context of statistical power, probably on Thursday. And these are the false negatives. And whereas the alpha value is the significance threshold, aka the type 1 error rate, it's the same thing as what we've learned before, but now that we know the term type 1 error and type 1 error rate, we now know that the alpha value is also that. The type 2 error rate is represented by the Greek letter beta. And in general, unless you're changing something like sample size, alpha and beta are kind of in a tug of war. When you try to lower the rate of type 1 error, you increase the rate of type 2 error. And likewise, if you try to reduce the rate of type 2 error, you increase the rate of type 1 error. So it's one of those, you can't always get what you want, and there's always trade-offs. And you won't be surprised to know at this point that the trade-offs are not chosen based on some kind of principled decision or some mathematical theorem. They're based on conventions people 100 years ago thought of. And here's this trade-off concept in action. Let's say that you are a researcher who's really, really concerned about getting false positives. You do not want to get a false positive. You don't want to publish any research that is later shown to not replicate, later shown to be not true. So you set your alpha value to 0.01. But if you do that, as we'll see in just a moment, you will actually increase your rate of type 2 errors by a lot. And the opposite would be true if we try to increase the rate of if we try to decrease our rate of type 2 errors, we'd increase our rate of type 1 errors. And this diagram here is a little bit confusing, and there's a Shiny app that visualizes it really well. But we have two distributions. One distribution represented by the alternative hypothesis, and one distribution represented by the null hypothesis. Don't get this confused with the distribution for the confidence intervals. This is a different way of conceptualizing it. These are both distributions of scores at this point. And we have our null hypothesis distribution, and we're also predicting an actual value and direction of our alternative hypothesis. So when doing what's called a power calculation or a power analysis, it's kind of like a baby's first power analysis. When you're trying to figure out something called statistical power, you can't just do what you did for the z-tests of a sample mean and say, you can't just have an alternative hypothesis that says, I think that the effect is going to be simply greater than the null hypothesis predicts, or less than the null hypothesis predicts, or either greater or less than. That was the extent of the directionality that the null hypothesis significance test asked you to do. It asked you to compare it asked you just to sort of predict higher or lower, or either higher or lower. However, when trying to calculate this thing called statistical power and later effect size, we have to actually go one step beyond that. And we have to not only predict the direction of the alternative hypothesis or research hypothesis relative to the null hypothesis, we also have to state what the mean of it is. Like, what do we predict the mean of the alternative hypothesis to be? And here, in this example, our null hypothesis distribution is centered on 25. So we predict our null hypothesis is centered on a mean of 25. And the alternative hypothesis is centered on a mean of 30. And if you just take a quick look at this diagram, which should be confusing, like you don't know what power is, why is the alpha value this, why is the beta represented by this line. So this line down the center is our sample mean converted into z units. Oh, sorry, that's actually, sorry, I misstated things. This line down the center is the critical z, which is something that we know based on our alpha value and whether we did a one-tailed test or a two-tailed test. So now let's go to the Shiny app. I will post the Shiny app in the chat so you can follow along with me. And I'll also post on Blackboard. Apologies for not doing that before. Shiny. There we go. So if you sort of to look at these things side by side, I don't know. So you see that this Shiny app, it's called Beta Probability. I'll post this in the chat. So you see that it's showing something similar, where it has two distributions, two normal distributions overlapping, and then a line down the center, and then some parts of the distributions where they overlap marked in one color and then marked in another color. Let me try to explain these things. So let me just increase the size of this. And I'll take you on a tour of this Shiny app that helps you visualize type 1 and type 2 errors. So just like the Shiny apps you've seen so far, there is a left-hand panel with various controls and options, and then there's a right-hand panel that actually visualizes the output of the options you chose. So for the sake of this, let's actually think about just a z-test of a sample mean, exactly what we've already learned about. We have a sample mean, we have a null hypothesis that's based on our understanding of what the kind of general population is like, or what we would expect if there was no effect. And just like in those hypothesis tests, well, in those hypothesis tests rather, you have to choose the kind of tail test you want to do. So even though I said you also have to specify a magnitude of the effect in one direction, we can actually we still have to choose tail test. So let's choose one-tailed upper first. So just leave it at the default. But let's just look what happens to the distribution when I go to one-tailed lower. See how when we're doing the one-tailed upper test, that red region, which is helpfully labeled the rejection region, is on the upper tail of this distribution on the left. And then when I choose lower tail, it shows the region of rejection over on the lower tail. That should be very, very familiar to you based on the standard normal distribution Shiny app, or your understanding of these tailed tests. And similarly, like you might guess, the two-tailed test actually has two regions of rejection, one on the lower tail and one on the upper tail. So let's just go to one-tailed upper for now. And here you can actually toggle between the different plots. So it might be confusing because this all looks like one plot over on the right, but you can see there's actually two distributions overlapping. And that's actually kind of complicated. So each of these distributions represents the null hypothesis and the alternative hypothesis. Let's actually turn off the alternative hypothesis for a second. So now we're just looking at the null hypothesis distribution. And now the tailed test makes a lot of sense, because for one-tailed upper test, for alpha equals 0.05, this is exactly kind of what we expect to see. Here's the top 5% of the distribution marked as a critical region, red region of rejection. And our critical value is listed here. It doesn't give us a z-value, but we know that it should be positive 1.96. Similarly, if we choose one-tailed lower and two-tailed, looks like that. So what we have here are three options below these choice of alpha levels. This option here just gives you the option to actually select your alpha value from this little slider, but the first option just lets you choose the alpha value or type 1 error rate from a list of presets. Let's use 0.05 for now because we're familiar with it. Here is one difference between what we've done before. We actually have to know the null hypothesis mean and our standard error of the mean. These are actually things we do know before. We're told the null hypothesis mean, and the standard error of the mean is something that we can calculate when we know the facts about the population. But here we actually choose the values. So if you wanted this to be 90 instead of 100, you can do that. And you see how the distribution shifts over a little bit. Now it's centered on 90 rather than 100. Or we could do 110. Notice how the plot showing the null hypothesis distribution shifts over depending on what the mean is. And you can also adjust the standard error of the mean. So here it looks like when the standard error of the mean is 5, the distribution looks like this. See, there's 90, 100, and 110. But if we change the standard error of the mean from 5 to 15, it's hard to see because the scale adjusted, but now the variance in this distribution is so much greater because I triple the standard error of the mean. So now instead of 5, we change it to 2. Here, when we change the standard error of the mean to 2, the distribution gets a lot skinnier, and we can actually see how skinny it is compared to the alternative hypothesis. For the sake of this power analysis and the Shiny app, just to make things simple, we're going to be assuming that both the null hypothesis distribution and the alternative hypothesis distribution are normally distributed and they have the same variance. So whenever I change the standard error of the mean here, it applies itself to both of the distributions. So let me just untoggle the alternative distribution. This assumption that of a normal distribution and this assumption of having the same variance for the null hypothesis and alternative hypothesis distributions, that is actually not a problem for a power analysis. There's a program I'm going to show you guys probably later in the semester called GPower, which is this neato software that lets you just calculate power in every possible situation, because from your computer's point of view, it's a very, very simple problem. But the whole point of today is that we learn the concept first. So we're going to start from a foundation that we're very familiar with, which is normal distributions. And for the sake of visualizing, let's imagine that both distributions for the null and alternative hypotheses have the same standard error. All right, so now that we've seen the null hypothesis distribution, let's visualize it once again with the alternative hypothesis distribution. We know from the fact that there's 105 as the alternative hypothesis mean that the alternative hypothesis distribution is going to be shifted to the right of our null hypothesis. And that's exactly what we see. When I turn it on and off, you see it pops there. So when it comes to our alpha value is always determined based on the proportion of the null hypothesis distribution that is above the critical value. So remember, we chose alpha value of 0.05, so our critical value is going to cut off the top 5% of our null hypothesis distribution, or if it was one-tailed lower tail, the bottom 5%. Let's stick with one-tailed upper for now. But then the alternative hypothesis distribution, I'm just going to untoggle the null hypothesis distribution. So we're only looking at the alternative hypothesis distribution. So remember, we are speculating, we are predicting an alternative hypothesis with a mean of 105. This is not something we've done before. We're actually predicting in advance what the alternative hypothesis, the actual mean of it is. So remember, we created a region of reject, we created our critical value based on our null hypothesis distribution. But then once we found that critical value, and it's marked by this dotted red line, if we were to untoggle the null hypothesis distribution and look just at the alternative hypothesis distribution, you see that there's this area of blue to the left of that critical value. And that blue area is actually beta. So beta is 0.74, which is about 75%. And if you look at the blue shaded area of this distribution, you can see that it's about 75%. And that's not an accident. So our beta value is about 0.74, and our alpha value is 0.05. Remember that we actually decided the alpha value in advance. And then based on the alpha value we chose, that determined what the beta value was. So that's generally going to be how it is. We always set the alpha value in advance, and then from that, we determine what the beta value is. So we set the type 1 error rate, and then we find out what the type 2 error rate is based on that type 1 error rate. All right, so why is it not the other way around? Why don't we set the beta value and then find the alpha value? The answer is we could do that, but I said earlier that we researchers care much more about the alpha value and controlling the type 1 error rate. So that's why we set it in advance and then see what the beta value turns out to be. So the whole idea of this power thing, and why I'm spending so much time playing around with it, and I encourage you to play around with it as well, is because I want you to see how different factors affect how this looks. So would you say that these two distributions, the null hypothesis distribution and the alternative hypothesis distribution, would you say that they have a lot of overlap or a little overlap? Just pop your answers in the chat. There really is no wrong answer to this. I just want your opinion. So I see a lot. Now it's interesting, it looks like most people say there's a lot of overlap, and you're correct, there is a lot. But now let's think of an example of something. Well, the thing is that there really is no correct way to answer this, because in the context of like a certain sort of variable, this amount of overlap could be huge, but in another context, it could be very small. So what can possibly affect the degree of overlap between the two distributions? So I will tell you that there are 3 options that you can choose on this left panel that will affect the degree of overlap. The first, well, I'll just tell you them, and I encourage you to like play around with them as well. The first is choosing whether a one-tailed test or a two-tailed test. Actually, let's do that last. Let's do the most obvious. Let's literally make the means more separate. So instead of a 5-point difference where the null hypothesis is 5 points below the alternative hypothesis mean, let's make it a 15-point difference by making this 90. So now there's a lot less overlap between those two distributions. And you'll notice that the alpha value has remained the same. The alpha value is still 5%, the top 5%, but that beta value has shrunk from about 74% of the alternative hypothesis distribution to only about 8.7%. So you can see that when there's less overlap, the rate of type 2 errors is lower. And this should make some sense, because let's say that you were, like, let's say you did have let's say that the alternative hypothesis was true, and the actual mean of your sample, or the population you were sampling from, was 105, and this was your, let's actually ignore numbers. Let's say that this distribution represents the distribution that you're actually sampling from, and the one on the left is the null hypothesis, which you're comparing your actual sample to. There's so little overlap that the chance of kind of confusing this distribution on the right for the distribution on the left is very unlikely. If you sampled, let's say, 5 random scores from the distribution on the left and 5 from the distribution on the right, you would very likely get very, very different means from both of those distributions, from both of the samples you took, because the distributions they came from are so different in terms of their mean. So another way that you can affect this beta value, let me just change this so that they're closer together again. So this is where we were originally, a 5-point difference. Another way that you can affect the degree of overlap, and by extension, the type 2 error rate, beta, visualized here as the blue shaded area, is instead of by making the difference between the null hypothesis mean and the alternative hypothesis mean greater, you can instead make the standard error of the mean lower. And I think we're going to see mathematically next time why it is that it shakes out this way, like why it is. So let me just change the standard error of the mean from 5 to 2, and let's see how the overlap between the two distributions changes. So I just changed from 5 to 2, and the overlap has shrunk from about 74% to about 19%. And you can think about it as both distributions getting skinnier, and more of the probability, well, the distribution itself, sort of more of the probability mass. It's hard to come up with a metaphor, but it being much more likely to get a score closer to the mean for both distributions. And that sort of shrinks them so that they're skinnier. And if they become skinnier and they're next to each other, their overlap will shrink, because their overlap is on the extremes. For the null hypothesis distribution, it's on the upper extreme, and for the alternative hypothesis, it's on the lower extreme. So the ways that you can affect the beta rate, the type 2 error rate, is by affecting the difference between the null and the alternative hypothesis mean, as well as the standard error. Those are the two main ways that you can affect your type 2 error rate. So when I said before there are 3 ways of affecting the type 2 error rate, that was actually wrong. I was misspeaking. There are 3 ways of affecting statistical power, which is related to type 2 error rate. So statistical power is very, very simple. I'm about to get to it it'll be the last thing I talk about today. But statistical power is simply 1 minus beta. So if beta is let's say beta is 0.19, let's just take off those last 2 decimals. That means that the power, statistical power, is 1 minus 0.19, which is 8.81 or 81%. And it's interesting that I happen to have come to a power that's an example that has a power of close to 80%, because just like we've always seen in the past, conventions about power, statistical power, hold that 80% is a good minimum amount of statistical power for a study. So I hope now this diagram makes a little bit more sense. You have our two distributions, and you have a critical z that's determined by the kind of tail test you're doing, as well as the alpha value that you chose up front. And the degree of overlap between the two distributions affects beta. And then beta affects power, since power is inversely proportional to the type 2 error rate. So that's the, I don't think I have enough slide about power, do I? All right, so there's definitely going to be more about power next time. But that is what statistical power is in a nutshell. When you do problems related to statistical power, you definitely want to have the Shiny app open. And the main reason you want to have the Shiny app open is because there are examples of statistical power where if you choose two-tailed instead of one-tailed, it starts looking like this. And if you're like me and you look at this, it gets pretty complicated because you have two regions of rejection, and technically that little area here is actually not a blue shaded area. So simply having software to tell you what the type 2 error rate is based on the tail test, alpha rate, difference between the two distribution means, and this the standard error for them both, it's just immensely helpful, because otherwise it's a nightmare. There used to be like tables for figuring out power and average differences. But this concept that I've just been referring to repeatedly as degree of overlap between two distributions, and how the kind of degree of overlap can be shrunk by either increasing the difference between the two means of the distributions, or by shrinking the standard error so that the distributions themselves get skinnier and the overlap decreases for that reason. That degree of overlap, that intuition you had when I asked you to estimate how much overlap there was between the two distributions in this example, that is kind of, that matches, your intuition there matches this thing called effect size. And effect size really is very, very similar to most people's intuitions about like what an effect is. So the effect is related to how much overlap there is between two distributions. And if there's very small overlap, we'll say there's a small effect size. If there's medium, we say a medium effect size. Large, we say a large effect size. Now the first answer, the first question you might have, well, the last question you'll have for today, because I'll be leaving you for today, is how do we figure out what small, medium, and large is? And the answer is going to either disappoint or be familiar to you, which is that there are conventions for statisticians saying that an effect is small, medium, or large. And next time when we get to the quantification of effect size using a term called D, or Cohen's D, which is the universal measure of effect size in statistics, we'll find that Cohen's D, when you calculate this, the effect size, if it's around 0.2, we say that's small. If it's around 0.5, we say it's medium. And around 0.8, we say it's large. And for Cohen's D, you can see that it is a simple fraction. It is the difference between the means of the two distributions divided by the standard deviation of both. We're assuming that both distributions have the same standard deviation. You'll divide it by that. If both distributions have different standard deviations, which is more common, you'll do what's called a pooled standard deviation, which is basically the average of it. But you see that D, Cohen's D, effect size, increases as the difference between the group means or population means increases. So if the difference between the two distributions shown here as solid lines and dotted lines, as it gets greater, then the top part of the fraction increases and d increases as well. Or if the standard deviation decreases, because when you decrease the bottom of a fraction, it means that when you do the division, the product will be, the quotient will be larger. So the two ways of affecting effect size is to increase the difference between your two groups, or by decreasing the variance of both groups. And we'll get to this question here, can Cohen's d be negative? Spoiler, it can't, just because that's a convention. So thanks for sticking by, guys. I'm sorry I could not attend class today in person. I'm amazed that I was able to speak this long without my voice giving out. Please let me know if you have any questions, and I will see you on Thursday.
Thank you.
Thank you.
Thanks, Professor.